Hi, this is Helia Hashemi from UMass Amherst, and this work is a collaboration with Hamed Zamani and Bruce Croft. Our work is about conversational search. Conversational search system aim to address user information needs through a natural conversation. This goal has been partially addressed in previous work, but with making several simplifying assumptions. However, this existing setting are still far away from the realistic scenario, which is mixed initiative and in which both user and system can take any permitted action at any time. Asking clarifying question is taking one step towards this realistic scenario, which is mixed initiative. To get some background, clarification has been studied in different tasks and domains such as speech recognition, dialect system, and more recently, conversational search. Two major related work to our work is one asking clarifying questions in open domain information seeking conversations by Ali and Nejadi et al. And generating clarifying question for information retrieval by Zamani et al. So, what's our work about? Our work is focusing on learning an effective representation for a user system conversation that involves clarification. So basically, whenever the system feels the performance is poor or it needs to collect more information about user information needs, it can go through asking more questions or clarifying question. This representation of the conversation history can be used in different underlying tasks such as retrieval and next clarification selection. So to solve this problem, we extended the transformer architecture by taking advantage of an external source. We called our model guided transformer because it is guided by an external source. So here is an example to show our motivation for this work. Here is the user initial query, tell me about migraine. And the system asks, are you looking for migraine symptoms? And the user answer is no. So far, in best case, the system knows that user is not looking for migraine symptoms, but it doesn't know what other possible intents could be. By looking into an external corpus, it could understand that migraine could treatments are one possible intent. The definition of migraine is one possible intent. The medicine for migraine is another possible intent. So by looking into an external resource, the system could understand what other potential intents could be for the user. Here is some background about transformer architecture. The foundation of transformer architecture is self-attention layer. So basically we have a self-attention layer and then add and norm, which is adopted from ResNet, and then a pointwise feed-forward layer, and then add and norm again. So in the self-attention layer, each token has three vectors: the query matrix, the key matrix, and the value matrix. Z is how the function of attention is calculated. So basically by multiplying vector Q and key, we achieve the attention weights, and with multiplying that into V vector, we updated the values of our representation. So this is how we achieve our model guided transformer, and how we updated and extended the traditional transformer model to gain guided transformer. So we have some external resource. We call them here source 1 to source n, and then we feed all of them into a multi-source self-attention layer, which is basically a self-attention layer, and it helps us to achieve a representation for all of these sources. Then and add a norm layer, and then we take these representation to take advantage of them in a new mechanism that we defined, multi-source cross-attention. We embed this multi-source cross-attention layer into the previous traditional form of transformer architecture. So multi-source cross-attention is a novel mechanism that we introduce in our work. Basically, we define another two vector q prime and k prime to calculate these external attention from our external source to the input of our model. Based on law of total probability and Bayesian rule, we can achieve the second formula from the first one. And intuitively, a multi-source cross-attention compute the attention weight from any token in an external source to any token in the input. So basically, we are calculating how important the tokens of our external source is for the tokens of our input. The weight of each external source is computed by another set of attention weights from their CLS token. This is the high-level architecture of our model, our end-to-end model. Basically, we have two guided transformer here for two tasks. We learn our model in a multitask setting. Our target task, which here could be re-ranking, and our second task, and the auxiliary task, which here is intent description identification. So we introduce a auxiliary task here just to help our training process, and we don't use it in the test phase. This auxiliary task here is intent description identification. Basically, we have the description of intent of a user, which our dataset provided for us, and then we compare it with the conversation text, and the system job is to identify whether this conversation is about this intent description or not. So basically, as you can see, we feed in our target task the conversation and document into a BERT model to learn representation, and we did same thing for our external sources, and the box that has same color, they share parameters. We also introduced task embedding to the input of our network because due to memory problems, we didn't use multiple BERT models. We reuse one BERT model for different tasks. So we introduced a task embedding just to facilitate the training process. And the loss of our model is a linear combination of loss of target task and auxiliary task. So here is some information about our dataset. We train and evaluate our model using Kulak dataset, which is publicly available. It is collected based on ClueWeb 09 category B. Here is some statistics about the dataset. Our experimental setup has been done on 5-fold cross-validation across topics, which in Kulak dataset is queries. We dedicate 3 folds for training, 1 fold for validation, and 1 fold for testing. We use the BERT-based model. We use the Galaga search engine for the first stage retrieval using query likelihood, and we filter out spam documents using the Waterloo spam scorer. For evaluation metrics, we use MRR and NDCG, and for external sources, generally speaking, we could use anything, but in these experiments, we use the top retrieved documents and all clarifying questions for the query that Kulak dataset provided for us. Here is results for document retrieval task. As you can see, the guided transformer model outperforms all baselines. As you can see, the multitask learning setting with the auxiliary task leads to significant improvement compared to all the baselines. When we use corpus of all clarifying question as an external source, we got better results in compared to a scenario when we use top ranked documents as the external resource. Of course, using both of them give us the best performance. Here are some plots about our results. As you can see, in with all the evaluation metrics, MRR, NDCG at 1, NDCG at 5, and NDCG at 20, the guided transformer outperforms all the baseline, and as we increase the turn of the conversation, the results get better. This table is about results for next clarification selection. The first line shows results when we don't use any clarification and we just use the initial user query, and at the bottom of the table you can see if we you can see the performance of the system if we use the worst and best clarification. As you can see, our model in multi-task setting outperforms all the baselines and achieves the best performance. Here is a case study. We introduce a win case, tie-dye, and a case that our model lose to the baseline. The first one, our model outperforms the baseline, and baseline here is BERT base model. So as you can see, the user only provide a minimal negative answer and not much more information. This is where our system, with looking into an external resource, can get better idea of what other possible intents could be. In the second and the third scenario, our model is not doing as good, and that's why the user also provide some some supportive information which makes it easier for the baseline model to retrieve answers. So now this is what we have done in nutshell. We extended the transformer architecture by leveraging external information sources and introduced guided transformer. We implemented guided transformer for the conversational search task, and we trained our end-to-end model using multitask learning by introducing an auxiliary task. So we at the end we evaluate our model on two target tasks: document ranking and next clarification selection using the Kulak dataset. Our model outperforms all. For future work, we can focus on studying the impact of various external information sources, like past interaction, user profile, contextual information, and so on. We will extend the model to fully mixed initiative multi-turn conversational setting, and we believe that guided transformer has application beyond conversational search, and it could be applied in many tasks beyond information retrieval. Thanks for listening. Please send me an email if you have any question. Thanks.